Well, we look now at a class of organic compounds called carbohydrates. Now, carbohydrates, or as we abbreviate them, CHOs, are an example of an organic compound of interest to forensic chemists. CHOs, or carbohydrates, are compounds of carbon, hydrogen, and oxygen. And they have the general formula C to the X, brackets, H2O, Y. Now, X and Y can be the same or different. Take, for example, glucose. We know that glucose is C6H12O6. Note that that's a carbon, hydrogen, and an oxygen atom in ratios of 6 to 12 to 6. Now that can be rearranged to fit that formula rule where you could write it as C6 brackets H2O 6. Now this fits the rule above, and in this instance X and Y are the same. In other instances you'll find that X and Y are different. For example, sucrose, which we will look at a little bit later on. This is one example of why glucose, by fitting that formula rule, can thus be classified as a carbohydrate. Now the simplest carbohydrates are called monosaccharides. Now mono means one, and saccharide is the word for sugar. So a monosaccharide is one sugar. Now you need to note that the word sugar is synonymous with carbohydrate. That means that carbohydrate, the word, is interchangeable with sugar. But this is true of chemistry. What's happened in society is that sugar has become a slang word that people use when referring to table sugar. Now table sugar is actually sucrose, which is a disaccharide that we'll look at in a moment. But this means that sucrose is indeed a sugar, but it's really a carbohydrate, and sucrose is certainly not the only sugar. Some examples of other sugars, or carbohydrates, are maltose, dextrose, fructose, glucose, galactose, and lactose. Note also then that O's as a suffix normally denotes a sugar or carbohydrate. So let's look at a monosaccharide, and we'll look at the monosaccharide glucose. Glucose is of intense importance for this course. It's really the building block of all the carbohydrates that we look at. Now there are two forms of glucose. We have beta glucose and alpha glucose. Beta glucose is the shape you have on the left of your screen now. If you look at beta glucose, you'll note that it's a ringed structure with carbons making a hexagon type shape with one oxygen inside the ring as well. As we examine it more closely, we have a methanol group sitting at the top of that carbon ring. We also have many hydroxide groups, but the one of interest to us as we examine beta glucose is the second red circle. Over on the right hand side, alpha glucose will now be formed. Watch carefully what happens to that hydroxide group that was previously circled. It switches places, such that now it is down the bottom of the ring. This hydroxide group, in relation to the methanol group at the top, is now opposite. When we say opposite, we see that it's on the opposite side of the ring. And a handy way to remember this is that alpha is opposite. I look there for the vowels. A for alpha, O for opposite. Alpha is opposite. When we're looking at the hydroxide group of interest, it's the hydroxide group that is bonded to what's called a carbonyl carbon. The carbonyl carbon is the carbon that is bonded both to the ringed oxygen and a hydroxide group. Examine very closely beta glucose on the left of screen. You'll note that the carbon atom that is circled is bonded both to the oxygen above it that is part of the ring, that's what we mean by a ringed oxygen, and also a hydroxide group. No other carbon in the whole complex is bonded to both a ringed oxygen and a hydroxide group. Thus, there is only one carbonyl carbon in beta glucose, and then have a look on the right of screen in alpha glucose, there's only one carbonyl carbon in alpha glucose. Therefore, the defining characteristic of beta glucose versus alpha glucose has to do with the hydroxide group on the carbonyl carbon. If the hydroxide group is on the same side as the methanol group, we have beta-glucose. That's the one on the left. If the hydroxide group bonded to the carbonyl carbon is on the opposite side of the ring to the methanol group, we have alpha-glucose. That's on the right of screen. Remember, alpha is opposite. You need to know and be able to recognize the difference between alpha and beta-glucose. You need to be able to draw alpha and beta-glucose. As an interesting point, note also the carbon that is opposite to the carbonyl carbon. What I mean there is go straight across the ring from right to left. It's the other carbon that has an OH hanging off it, but is not joined to the ringed O. That OH group is always down. If it was to be up on the same side as the methanol group, we would have galactose. We don't examine galactose in this course, so it's important for you to simply know that when you're drawing glucose, that particular OH group must be down the bottom or on the opposite side always. Another thing to note too of glucose is that it has a hexo shape. Now hex here stands for the shape, or hexagon. So it's a hexagon shaped sugar. That's O's. Hex here does not refer to the number of carbons. It's just a fluke that glucose has 6 carbons. The hex is in reference to shape. This will become more clear as we examine fructose, another important monosaccharide. Fructose here is labelled as beta fructose. Now fructose also has a carbonyl carbon, the arrows pointing to where it is. Note in this diagram, the carbons are not all drawn in. Chemists will often leave out the ringed carbons, and it's a given that at every point of the hexagon or the pentagon or whatever ring structure you have, a carbon exists and you don't have to draw it. So at that junction of those bonds, where the red arrow is pointing, there is a carbon atom. And it's a carbonyl. Why? Well, it's joined to a ringed oxygen and a OH group. And it's the only one that does that. So it's the only carbonyl carbon. Note also the shape of fructose. It is a pentose shape. Count the carbons for yourself now and tell me how many you get. 6, isn't it? So pentose is in reference to the shape of fructose, not the number of carbons. It's in the shape of a pentagon, so we call it a pentose monosaccharide. You need to know fructose and alpha and beta glucose as the 2 examples of monosaccharides. Moving on from monosaccharides, we get to the next level of complexity, disaccharides. Di means 2, saccharide means sugars. Thus, a disaccharide is composed of 2 sugars. The only disaccharide you are required to know is sucrose. So that's the only one we will look at. Sucrose is the product of alpha glucose combining with beta fructose via a condensation reaction. This means that when sucrose forms, one water molecule of water is produced or emitted. And this happens in exactly the same way as condensation polymerization reactions that we did in our first core unit. Remember that a condensation reaction occurs when 2 molecules join together with the emission of a smaller molecule, usually water. So sucrose is an example of a disaccharide, and it occurs when glucose is added to fructose. Have a look at the glucose molecule on the left, locate the carbonyl carbon, which is the rightmost carbon in the ring. It's bonded to a ringed oxygen and a hydroxide group, and the hydroxide group is on the opposite side to the methanol group at the top. Alpha is opposite, so we have alpha glucose adding to fructose. What happens is that the OH group comes into contact with the OH on the fructose molecule, and they join around the remaining oxygen and omit a water molecule. This is a condensation reaction, and the product is sucrose down the bottom. Sucrose is the only disaccharide you need to know. You must be able to recognize its structural formula. Note that the hexose of glucose is on the left, and the pentose of fructose is on the right. Interestingly, glucose and fructose, if you added up all their atoms, have identical molecular formulae, C6H12O6. The only difference is in their structure, but that difference is significant, and fructose is the sugar usually associated with fruits. Now, sucrose is the resulting disaccharide and forms with the emission of a small water molecule. The definition, therefore, of a disaccharide is that it can be hydrolyzed into two monosaccharides. Now, that simply means that sucrose can be split back into its parent monosaccharides, glucose and fructose. Now, in the body, this involves enzymes, so you have enzymatic activity that can break sucrose down into glucose and fructose. That means that when you put some sugar in your coffee, you are able to break it down further and utilize the sugars for energy. In the laboratory, we can achieve this by heating the disaccharide gently with an aqueous acidic solution. Now, remember, aqueous means something is in water, so that's where you get the water from. And here the acid is acting as a catalyst. So the acid is playing the part of an enzyme in the laboratory. It's getting involved in the reaction, but does not alter the reactants or products in any way. So it's a catalyst in this reaction. This catalyst, which is a strong aqueous solution of a strong acid, allows water to split apart, donating back a hydroxide and a hydrogen to the parent molecules of glucose and fructose so that they can then exist again on their own. That's what hydrolysis is. It's the reverse of condensation. Here it is schematically. There is a nice molecule of sucrose for you. Note that it's bonded around the central oxygen atom. If I introduce some water and H+, indicative of acid, that H+ allows the water molecule to come into contact with the centralized oxygen atom. Thus, glucose is formed as OH is added back to where the carbonyl-carbon bond hangs down, and we have fructose, as a similar thing happens with the hydrogen and the oxygen interacting with fructose, and the acid is the catalyst that allows this to happen. So if I reintroduce water to a disaccharide in the presence of a catalyst, whether it's an enzyme or acid, I can reform the parent monosaccharides by hydrating or hydrolyzing the disaccharide. Now, the next level and final level of complexity that we look at introduces polysaccharides. Poly means many, and saccharide is sugars. Thus, a polysaccharide is composed of many sugars. Now, there are three polysaccharides that you need to know. The first one is cellulose, plants, starch from plants, and glycogen, which is in animals. All of these are polymers of glucose. In other words, glucose can be arranged in three different ways in order to produce these three different polysaccharides. Let's look at cellulose first. Cellulose is the main structural component of plant tissue. During photosynthesis, carbon dioxide and water combine to produce glucose, and this glucose then undergoes polymerization into cellulose. Now, it's beta-glucose that is the parent monomer of cellulose, not alpha-glucose. So you must remember that beta-glucose forms cellulose. Now, cellulose is insoluble, and it's typically 2,000 to 4,000 glucose units in length. And it has no chain branching, so it's a long, linear, fibrous material of substantial size, which means that it does not dissolve. This is how cellulose forms. Have a look at that glucose molecule. Have a look at the hydroxide group in orange that's attached to the carbonyl carbon. That hydroxide group is on the same side of the ring as the methanol group. If it's on the same side, we have beta glucose. Of course, beta glucose is responsible for the formation of cellulose. If I bring another beta glucose into the proximity of the first one, you can see how the H and the O of the neighbouring beta glucose molecule combine with the H and the O of the first neighbouring glucose molecule, and they emit water. Now, if you emit 2 hydrogens and 1 oxygen, you'll be left with 1 oxygen. This is shown schematically now on the right-hand side. As OH is emitted and H is emitted, there's only 1 O left over, which becomes the new bond for cellulose. Every time 2 molecules of beta-glucose come into proximity and form a bond around the O, 1 molecule of H2O is emitted. An important part of the formation of cellulose is shown schematically here. Have a look at the top molecule of cellulose. We know that the beta molecule must flip every second molecule in order for the hydroxide groups to line up. And so it flips, alternating, such that every time that occurs, it joins a bond around the centralized oxygen atom and water is emitted. Now, cellulose can hydrogen bond with neighbouring cellulose strands. So the bottom cellulose strand is attracted via hydrogen bonding to the topmost cellulose strand. This is another reason why cellulose is very resistant to water attack, because it's a long fibrous chain in a linear form strongly wrapped around other fibrous chains with very strong hydrogen bonding. Here's another schematic representation of cellulose. Note in figure A the flipping of the beta-glucose molecule. Every second one is upside down. This has occurred because it's necessary for the geometry of the hydroxide groups to come into proximity when the bonding occurs. Structure B below shows a more accurate geometrical representation of cellulose. This is a buckled form which tries to show the different angles around the carbon, oxygen and hydrogen bonds. You need to be able to recognise cellulose in both of these forms. Figure A is easy to recognise. B is also easy to recognise simply because you have the alternating flipping second molecules, and you can recognise the ringed oxygen, the hexose shape, and the presence of the methanol groups. We move now to the second polysaccharide, starch. Now, it's another plant tissue and it's a polymer of alpha glucose. So this sets it apart from cellulose because cellulose is beta glucose, starch is alpha glucose. Now, starch forms when alpha glucose monomers polymerize via condensation reactions. There are 2 types of starch that have very different properties. The first type of starch is called amylose. Now, when starch from plants is warmed in water, about 20% of it dissolves. Now, this soluble starch is different from the other 80% of insoluble starch, and we call soluble starch amylose. Amylose is a polymer of alpha glucose. Now, these alpha glucose monomers are arrayed in a globular form and they do not have chain side branching. Amylose has relatively short chain lengths, only about 60 to 300 glucose units per molecule. Now, because it has small chain length and no chain branching off the side, amylose is soluble. Here's how amylose forms. On the left-hand side, you have glucose. On the right-hand side, you have glucose. Locate the carbonyl carbon. It's bonded to the ringed oxygen and has a hydroxide group. Now, the hydroxide group is on the opposite side of the ring to the methanol group. Therefore, we have alpha glucose. This means that the hydroxide groups are already lined up. They can condense, emitting a water molecule, and they can then form the polymer or polysaccharide amylose. Note how amylose starch lines up in exactly the same way as cellulose, but due to the alpha-glucose monomers, there is no need for each glucose unit to flip in order to line the hydroxide groups up. Thus, we have amylose as a chain structure, figure A, all lining up with no flipping of the glucose molecule. Now, the globular shape of amylose is shown below. This is due to opposing forces in the many COC bonds forcing the molecule into an arced shape that folds around on itself. This is amylose. Look carefully at it. The glucose monomers are not flipping. Therefore, we have glucose lining up via an alpha bond around each centralized oxygen. The shape of those carbon-oxygen-carbon bonds forces it into an arced form, which will continually arc round and round and form what's called a globular formation of amylose. The second type of starch is called amylopectin. When starch from plants is warmed in water, about 20% of it dissolves and 80% does not. Now, the 80% is insoluble, called amylopectin. Now, amylopectin is also a polymer of alpha-glucose. So think of it like this. Amylose and amylopectin are alpha-glucose, all A's. The difference between amylopectin and amylose is that amylopectin has significant side chain branching. This means that not only does it form a linear structure, but off the side you will have branches forming, in a very similar way to LDPE from Unit 1, low-density polyethylene. Amylopectin is much longer than amylose, and it has chain lengths of about 300 to 6,000 glucose units per molecule. Another way that I remember the difference is that amylopectin is a longer word, so amylopectin is a longer molecule than amylose. Subsequently, because it's got chain branching and it's a big molecule, amylopectin is insoluble. The third type of polysaccharide you need to know is glycogen. Glycogen is sometimes called animal starch because it's so similar to starch. It's also a polymer of alpha-glucose, but it's even more highly branched than amylopectin. Glycogen, however, is soluble. That's the only difference of glycogen to amylopectin. Glycogen's soluble. The reason being is that it's a much smaller molecule. It's usually less than 300 glucose units in length. The only molecular difference to amylopectin is its size. Therefore, the only physical difference is its solubility. Now, glycogen is found in the muscles of animals, and it's the way that animals store the energy that they have received from consuming plant matter. When they consume starch, the body breaks it down into glucose molecules, and then the body will reform it back into glycogen with a lot of chain branching and transport it to the muscles. So again, glycogen is essentially long chains of glucose which first came from plant matter, which was first produced by plants via photosynthesis. Now, glycogen and amylopectin have side branching in exactly the same way. Have a look at that diagrammatic representation on the screen. They are alpha bonded glucose molecules. They're in a linear form, so at this stage we could say that that's a small section of amylose. No side chain branching and alpha-glucose. That's amylose. However, if we introduce another alpha-glucose molecule and the hydroxide comes into contact with the hydroxide on the methanol group, as represented by the red arrow, we can get a condensation reaction occurring up here. The hydroxide group disappears, a new centralized O bond forms around the carbonyl carbon of the new glucose alpha molecule that's come into contact, and water is emitted. We now have a side branch. So now we're not viewing amylose, we're viewing amylopectin or glycogen. At this stage, the only way to tell the difference between glycogen and amylopectin would be to examine the length of the molecule, the size of the molecule, and the number of side chain branches. If it had significantly more side chain branching and was a smaller molecule according to its molecular weight, we would conclude that it's glycogen. Likewise, if it had been sourced from an animal muscle, we would know that it was glycogen. If, however, we had up to 6,000 glucose monomers, we had some chain branching but not as much as glycogen, and we knew that it had come from a plant tissue, we would conclude that what we're looking at here in figure A is amylopectin. We could then test it for solubility. If it was soluble, we would be dealing with glycogen. If it was an insoluble, chain branching alpha glucose polysaccharide, we would conclude that it's amylopectin. Some fairly complex information there, but we must know it. Finally, energy from polysaccharides. We see that glycogen, starch and cellulose must be hydrolyzed back into glucose before they can be used for energy. Now, enzymes do this in the human body, but humans don't have the ability to destroy beta linkages. We don't have the enzymes necessary. Therefore, cellulose can't be broken down by humans. So if we consume cellulose, it will simply pass through our gastrointestinal tract and leave our body as a solid stool. Ruminants actually employ bacteria that contain beta-destroying enzymes to do the job of breaking down cellulose, and therefore we see that ruminant animals like cows and sheep are able to consume cellulose in the form of grass and leaves and so forth. Humans do, however, have alpha-destroying enzymes, and we can therefore hydrolyze starch to glucose for energy because starch is bonded via an alpha linkage. In a laboratory, polysaccharides can be refluxed in the same way that we would reflux an ester, and it's refluxed with a strong acid in order to achieve hydrolysis in the same way as was detailed for sucrose.